In this video we shall briefly introduce our paper on adiabatic dynamics of edge waves in photonic graphene. This paper studies light propagation in photonic lattices with a honeycomb background, known as photonic graphene due to its similarities to material graphene. Recently it was shown in the reference Nature paper that by introducing edges in suitable relay guides in the direction of propagation, unidirectional edge wave propagation at optical frequencies occurs in photonic graphene. The system is described analytically by the lattice nonlinear Schrödinger equation shown as the top equation. Assuming that the minima of the potential V are relatively deep, the system is described well by a tight binding model on a semi-infinite honeycomb lattice, as shown in the bottom figure. The vector field A represents the periodic change of the refractive index in the direction of propagation, and plays the role of a pseudo-magnetic field. Taking this pseudo-field to be circular, as shown in the left figure, the edge waves were found to be nearly immune to backscattering. In this sense, photonic graphene exhibits the hallmarks of Floquet topological insulators. Our current paper analyzes the asymptotic regime where the pseudo-field A varies slowly, or equivalently adiabatically. This may be contrasted with the rapidly varying case addressed in the reference PRA paper, also authored by us. By using Floquet theory, explicit formulae for the dispersion relation of traveling edge modes are obtained from an asymptotic theory. This slide shows a dispersion relation computed using a circular pseudo-field, as shown in the top figure. In this case, as shown in the left figure, the dispersion relation of edge modes crosses the horizontal axis once, or equivalently is topologically nontrivial. The full dispersion relation including both edge and bulk modes is shown in the right figure. This slide shows a dispersion relation computed using a figure 8 pseudo-field, as shown in the top figure. In this case, as shown in the left figure, the dispersion relation of edge modes does not cross the horizontal axis, or equivalently is topologically trivial. The full dispersion relation including both edge and bulk modes is shown in the right figure. In both cases, the asymptotic prediction shown in black agrees well with the numerical computation shown in blue. This slide shows that there are quasi-edge modes which persist only for part of the period. As shown in the left figure, the two-dimensional quasi-edge mode disintegrates into the bulk after a critical time. As shown in the right figure, the time evolution of this two-dimensional mode before disintegration is described well by a time-dependent one-dimensional linear Schrödinger equation along the edge. The presence of these quasi-edge modes represents the new dynamics introduced by the adiabatic variation of the pseudo-field at the linear level. This slide shows that the effect of weak nonlinearity on edge wave propagation. As shown in the left figure, there are extremely robust two-dimensional edge modes that appear to be immune to backscattering when the dispersion relation is topologically nontrivial. As shown in the right figure, the time evolution of the two-dimensional edge mode is described well by a time-dependent one-dimensional nonlinear Schrödinger equation along the edge. The time dependence of the coefficients of this nonlinear Schrödinger equation represents the new dynamics introduced by adiabatic variation of the pseudo-field at the nonlinear level. Thank you for your attention. Please see our paper for more details.